Hello everyone, and welcome back to another stream of Advanced Pathophysiology. Today we're talking about Chapter 44, the structure and function of the musculoskeletal system. This should be a relatively brief chapter, so I think we'll be pushing right on through this today. So without much further ado, let's jump right on in. The way an individual functions in daily life, moves, or manipulates objects physically depends on the integrity of the musculoskeletal system. The musculoskeletal system actually consists of the following two systems: the skeleton composed of bones and joints, and soft tissue, skeletal muscle, tendons, and ligaments. Each of the systems contributes to mobility. The skeleton supports the body and provides leverage to the skeletal muscles so that movement of various parts of the body is possible. Contraction of the skeletal muscles and bending or rotation at the joints facilitates movement of the various body parts. So, the structure and function of the bones. Bones give form to the body, support tissue, and permit movement by providing points of attachment for muscles. Many bones meet in movable joints that determine the type and extent of movement possible. Bones also protect many of the body's vital organs. For example, bones of the skull, thorax, and pelvis are hard exterior shields that protect the brain, heart, lungs, and reproductive and urinary organs. Bone marrow is one of the sources of the mesenchymal stem cells. These non-hematopoietic stem cells consist of small proportions of the stromal cell population in the bone marrow and can generate bone cells, cartilage cells, and fat cells that support the formation of blood and fibrous connective tissue. Within certain bones, the marrow cavities also serve as storage sites for the hematopoietic stem cells that form both blood and immune cells. In adults, blood cells originate exclusively in the marrow cavities of the skull, vertebra, ribs, sternum, shoulder, and pelvis. Bones also have the crucial role in the mineral homeostasis that is essential for the performance of many delicate cellular mechanisms, have a role in hormone homeostasis, and assist in maintaining normal immunologic function. So here we're taking a look at a bone, and here's the marrow, the hematopoietic and mesenchymal stromal cell differentiation. So hit pause if you want to look deeper into again anatomy. Elements of the bone tissue. Mature bone is rigid yet flexible connective tissue consisting of cells, fibers, and homogeneous gelatinous medium termed ground substance, and large amounts of crystallized minerals, mainly calcium, that give bone its rigidity. Ground substance consists of proteoglycans and hyaluronic acid secreted by chondroblasts. The structural elements of bone are summarized again on table 44.1. So here we have a table, the structural elements of bone. So we have the structural element and its associative function. Osteoblasts, osteocytes, osteoclasts. The bone matrix, your collagen fibers, your proteoglycans, your bone morphogenic proteins, your glycoproteins, your sialoprotein, osteocalcin, laminin, osteonectin, albumin, alpha-glycoproteins, minerals, calcium, phosphate, alkaline phosphate, and vitamins D and K. Again, please pause so you can see or read their individual functions. I know I kind of ran through these relatively quickly. Bone cells enable bone to grow, repair itself, change shape, and continuously synthesize new bone, tissue, and reabsorb, dissolve, or digest old tissue. The fibers in the bone are made of collagen, which gives both its tensile strength. Ground substance acts as a medium for the diffusion of nutrients, oxygen, metabolic wastes, biochemical and minerals between bone tissue and blood vessels. Bone formation begins during the embryonic development, when the mesenchymal stem cells begin differentiating into either chondrocytes or pre-osteoblasts. Endochondral ossification and intramembranous ossification are two major mechanisms responsible for normal bone development. Endochondral ossification occurs when the mesenchymal or loose tissue found during embryonic development stem cells begin differentiating into chondrocytes, which in turn develop a mineralized cartilage scaffold that allows formation of osteoblasts. Long bones and most other bone elements are formed this way. Intramembranous ossification is responsible for the development of skull and flat bones. With intramembranous ossification, mesenchymal stem cells differentiate into the pre-osteoblast line that forms osteoblasts without any cartilage framework. Multiple factors influence normal bone formation, maintenance, and remodeling. Bone morphogenic proteins are members of the transforming growth factor beta superfamily, and BMPs, which is a bone morphogenic protein, play a major role in bone formation. This group is primarily responsible for the initiation, differentiation, and commitment of precursor cells into osteoblasts. Your transforming growth factor beta signals are transmitted across the plasma membrane, combined with certain proteins that act as transcription factors, and then form specific receptors known as R-SMADs. These receptors in turn initiate intracellular signaling, interact with other transcription factors, and regulate other factors that are important in osteoblast formation, function, and maintenance. Crosstalk between signaling pathways is critical in the regulation of osteoblasts. BMPs have multiple crucial functions in the skeletal system. Activities are regulated at different molecular levels, summarized here at table 44.2, and the roles of several important BMPs. So, your bone morphogenic proteins and their known functions. Pause. Can't make this more important. Pause here, write these down, know their functions. Your BMP1 involved in cartilage development is actually a metalloprotease, key role in extracellular matrix formation. BMP2 induces bone and cartilage formation, osteoblast differentiation, bone healing. BMP3 induces bone formation. BMP4 regulates formation of teeth, limb, and bone. BMP5 involved in cartilage development. BMP6 found in osteoblasts helps maintain adult joint integrity, accelerates bone repair. BMP7 has a major role in osteoblast differentiation, chondrocyte formation, fracture healing, important in renal development and repair. BMP8A, BMP8A involved in bone and cartilage development, upregulated in fracture non-union. BMP9 induces osteogenesis in mature osteoblasts. BMP10 plays a role in development of the heart. BMP12 involved in tendon and ligament formation. BMP13 involved in cartilage development, again, but also has involvement in tendon and ligament repair. BMP14 assists in bone and tendon healing, as well as cartilage formation. These are going to be important. Your W and T genes belong 2. A large family of protein signaling factors that are required for the development of body systems, including the musculoskeletal system. They play a significant role in forming bone, developing bone mass, remodeling bone, and healing fractures. WNT signaling regulates production and differentiation of osteoblasts and osteoclasts and affects bone mass and density, joint formation, fracture repair, bone remodeling, and some bone diseases. Other important elements responsible for bone formation and homeostasis are presented here in Table 44.3. Again, really important. Make sure you hit pause. Write them down, make flashcards, any way that helps you remember these things. Selected factors affecting bone formation and homeostasis. That's your transforming growth factor beta, your platelet-derived growth factor, your fibroblast growth factor 2, insulin-like growth factor, your IGF-1, IGF-2, SMAD proteins, bone morphogenic proteins, tumor necrosing factor, osteoproteogerins, and the list keeps going. So again, hit pause maybe here. Your receptor activator of nuclear factor, your bone morphogenic protein antagonists, your noggin, gremlin, twisted gastrulation, activin, inhibin, leptin, that WNT pathway, your WNT antagonist, your Dickhoff family or hard-headed family, sclerostin, and your transcription factors, nuclear factor of activated Kupffer beta cells, or NFK beta, your matrix metalloproteinases, family of endopeptidases that include collagenases, gelatinases, stromylysins, and matrolysins, a disintegrin and metalloproteins, disintegrin and metalloproteinases with thrombospondin motifs, your cysteine protease, your cathepsin, your MMP inhibitors, your tetracyclines, and your tissue inhibitor of metalloproteinases. So again, please hit pause. I'm going to go back up a little bit here so you can kind of get spots to pause at. Pause here, make some flashcards. I'd say here's as good of a spot as I need to pause one more time. Go ahead and pause here because here it also jumps into that transcription factors. There you go. Pause one last time here. In mature bone, the formation of new tissue begins with the production of an organic matrix by the bone cells. This bone matrix consists of ground substances, collagen, and other proteins that take part in bone formation and maintenance. The next step in bone formation is calcification. When minerals are deposited and crystallize, minerals bind tightly to collagen fibers, producing tensile and compressional strength of bone, and withstand pressure and weight bearing. Your bone cells. Bone contains three types of cells: your osteoblasts, your osteocytes, and your osteoclasts. Osteoblasts are the bone-forming cells, whose primary function is to lay down new bone. Once this function is complete, osteoblasts become osteocytes that are embedded in bone, comprising 90 to 95% of bone cells. Osteocytes develop dendritic processes that extend either to the bone surface or to the bone's vascular space. Osteocytes help maintain bone by signaling osteoblasts and osteoclasts to form and resorb bone. Osteoclasts are the major bone resorbing cells responsible for remodeling. So here you're taking a look at different types of bone cells. So if we're talking specifically, osteoblast originate from the mesenchymal stem cells. Bone formation is initiated by osteoblasts. Mature osteoblasts produce an organic calcium phosphate, which is converted to hydroxyapatite and an organic matrix that is compromised mainly by type 1 collagen. Once this process is complete, osteoblasts deposit new bone in response to the bone resorbed by osteoclasts. Osteoblasts and osteocytes control osteoclast differentiation and bone resorption by producing receptor activator of nuclear factor K beta ligand and osteoprotegerin. Osteoclasts trigger an osteoblastic response to couple bone formation to bone resorption during bone remodeling. The net result is continuous renewal of the skeletal system. Bone remodeling and bone modeling and bone remodeling are the process that allow the skeleton to adapt to environmental challenges and to regulate mineral metabolism. Osteoblasts cause the formation of new bone and the orderly mineralization of bone matrix by concentrating some of the plasma proteins found in the bone matrix and by facilitating the deposit and exchange of calcium and other ions at the site. Enzymes, signaling proteins, and growth factors, including bone morphogenic proteins, and other members of the transforming growth factor beta superfamily are critical components of bone formation, maintenance, and remodeling. So here at this table, we see the effects of selected cytokines on skeletal tissue. So you have your transforming growth factor beta, transforming growth factor alpha on epidermal growth factor, insulin-like growth factor, fibroblast growth factor, platelet-derived growth factor, colony-stimulating factor, interferon gamma, tumor necrosis factor, and interleukins 1, 3, and 6. So here you can see where there's bone and cartilage formation or resorption. Osteoblasts are active on the outer surface of bones, where they form a single layer of cells. They are responsive to parathyroid hormone and produce a protein called osteocalcin when stimulated by the 1,2,5-dihydroxyvitamin D3. Osteoblasts initiate the formation of new bone by their synthesis of osteoid. The mechanism of osteoblast stimulation is reported to be production of so-called coupling factors generated during the resorption process. Osteoblasts alter levels of RANKL or RANKL and osteoprotegerin. The balance of these two cytokines determine overall osteoclast formation. As new bone is formed, it is shaped and remodeled through TGF-beta, or tumor growth factor beta, as well as other plasma proteins found in the bone. So that's, strictly speaking, osteoblasts. Now, strictly speaking, osteocytes. Osteocytes, the most abundant cell in the bone, are transformed osteoblasts that become trapped or surrounded in osteoid as it hardens because of minerals that enter during ossification. It is the final differentiation stage for an osteoblast. The osteocyte is within a space in the hardened bone matrix called a lacuna. Within the mineralized matrix, osteocytes are interconnected by a network of dendritic cytoplasmic processes through tunnels known as canaliculi. These canaliculi radiate from each lacuna and contain cell processes from the resident osteocyte. thereby enabling it to form gap junctions with adjacent osteocytes. Within this microenvironment, osteocytes detect mechanical forces and help to control calcium and phosphate levels. One of the osteocyte's primary functions is to act as a mechanoreceptor, responding to changes in weight bearing or other stressors on bone. Lying within the lacunae are the osteocyte's primary cilia, which are likely the primary mechanoreceptors in bone. Once changes, such as mechanical stress, hormonal imbalances, loading or unloading, in bone are detected by the osteocyte's mechanoreceptors, multiple molecular signals are produced and the process of bone remodeling begins. Osteocytes communicate with other bone cells and instruct both osteoblasts and osteoclasts about when and where to form and resorb bone, concentrate nutrients in the matrix, regulate bone mass and minerals, and secrete other proteins such as sclerostin and fibroblast growth factor 23, which influence mineral metabolism. Sclerostin inhibits osteoblasts, thus reducing bone formation. Additionally, osteocytes seem to function as endocrine receptors in regulating bone metabolism and are prime target cells of parathyroid hormone. Through exchanges between these cells, hormone catalysts, and minerals, optimal levels of calcium, phosphorus, and other minerals are maintained in blood plasma. That leads us to osteoclasts. Derived from the hematopoietic monocyte macrophage lineage, osteoclasts are terminally differentiated multinucleated bone cells and are responsible for bone resorption. Osteoclasts migrate over bone surfaces to resorption areas that have been prepared and stripped of osteoid by enzymes, such as collagenases produced by osteoblasts in the presence of parathyroid hormone, which are necessary for the resorptive process. Osteoclasts travel over the prepared bone surfaces, creating irregular scalloped cavities, known as house-shaped lacunae or resorption lacunae, as they resorb bone areas and then acidify hydroxyapatite in order to dissolve it. A specific area of the cell membrane adjacent to the bone surface forms deep and irregular foldings. These foldings, known as the ruffled border, greatly increase the surface area of cells under their scalloped or ruffled borders. Osteoclasts resorb bone by secretion of hydrochloric acid, acid proteases, and matrix metalloproteinases that help digest collagen, along with the action of cytokines. Osteoclasts also resorb bone through the action of lysosomes, filled with hydrolytic enzymes in their mitochondria. Osteoclasts bind to the bone surface through attachments called podosomes, which are foot-like structures that cluster together along a sealing membrane that forms a belt containing multiple protein enzymes and integrin receptors. Once resorption is complete, the osteoclasts retract and loosen from the bone surface under the ruffled border through the action of calcitonin. Calcitonin binds to receptors areas of the osteoclasts' cell membranes to effectively loosen the osteoclasts from the bone surface. Once resorption is completed, osteoclasts disappear by the process of degeneration, either by reverting to the form of their parent cells or by undergoing cell movement away from the site, in which the osteoclast becomes an inactive or resting osteoclast. In addition to resorption of bone, osteoclasts assist the endocrine and renal system in maintaining appropriate serum calcium and phosphorus levels. Osteoclasts also appear to have a role in the body's immune response. So that was different cell types. So now we can talk about the OPG, RANKL, and RANK system. So OPG stands for osteoproteogenerin, which is a glycoprotein that belonging to the tumor necrosis factor superfamily and inhibits bone remodeling resorption by inhibiting osteoclast formation. Numerous cells, including osteoblasts and osteocytes, produce it. OPG is key in the interaction between osteoblast and osteoclast. Osteoblast and osteoclast cooperate to maintain normal bone homeostasis. Your rankle is an essential cytokine needed for the formation and activation of osteoclasts. Rankle increases bone loss. OPG decreases bone loss because when it is activated, it promotes bone formation. When rankle binds to its receptor rank on the osteoclast precursor cells, it triggers their proliferation and increases bone resorption. OPG, secreted by osteoblasts and B lymphocytes, serves as a decoy by binding to rank, preventing rankle binding to rank, and thereby preventing bone resorption. Therefore, the overall balance between your rankle and OPG determines the amount of bone loss as regulated by cytokines and hormones. Alterations of the rankle, rank, and OPG system can lead to dysregulation and pathologic conditions, including primary osteoporosis, immune-mediated bone disease, malignant bone disorders, and inherited skeletal disease. It is worth noting that a dimethyl sulfoxide, an FDA-approved organosulfur solvent, is reported to have osteoclast inhibiting properties. In a recent study, data shows that 1% of the dimethyl sulfoxide significantly inhibited rankle-induced osteoclastogenesis. Specifically, DMSO inhibited both differentiation and function of osteoclasts. This is an important finding because it presents the potential use of DMSO for treatment of bone diseases related to increased osteoclast proliferation, such as osteoporosis. One study demonstrated that daily injections of DMSO inhibited estrogen deficiency-induced osteopenia in rats by inhibiting the function of the osteoclasts. So, our bone matrix. Bone matrix is made of the extracellular elements of bone tissue. Bone matrix is composed of an organic component, known as osteoid, and a mineral component. Osteoid is comprised of predominantly type 1 collagen, with small amounts of glycose aminoglycans and other proteins. So if you want to know everything that is in the bone matrix, read box 44.1, hit that pause button. The major inorganic components of the calcium and phosphate minerals. Other parts of the bone matrix are the proteins, carbohydrate protein complexes, and ground substances. Water comprises 5 to 8% of that matrix as well, leading us to collagen fibers. Collagen fibers make up the bulk of the bone matrix. They are formed as follows. Osteoblasts synthesize and secrete type 1 collagen and osteocalcin. Collagen molecules assemble into 3 thin chains to form fibrils. Fibrils organize into the staggered pattern, with each fibril overlapping its nearest neighbor by about 1/4 its length. This creates gaps into which mineral crystals are deposited. After a mineral deposition, fibrils interlink and twist to form rope-like fibers. The fibers then join to form the framework that gives bones its tensile and supportive strength. So, collagen is the most abundant macromolecule in the body, accounting for approximately 1/3 of all protein and providing the structural framework for nearly all tissues. Collagen is one of the extracellular components, along with proteoglycans, and non-collagenous matrix proteins of articular cartilage. To date, more than 20 types of collagen have been identified, though all their functions are not yet known. Cartilage-specific collagens include types 2, 6, 9, 10, and 11. Type 9 collagen is thought to be the glue that holds together the type 2 collagen scaffold of articular cartilage, helps maintain the structural integrity of cartilage, and resists tensile forces on joint cartilage. Type 11 regulates the fibril diameter of type 2 cartilage. Degradation of type 9 collagen by proteolytic enzymes has been seen in the early stages of osteoarthritis and rheumatoid arthritis. Researchers have proposed that this degradation or unplugging may be the mechanism for the degenerative changes seen in osteoarthritic and rheumatoid cartilage. Table 44.5 gives the musculoskeletal distribution of other types of collagen. So a good spot to stop and hit pause, because here we are looking at all the different types of collagen in musculoskeletal tissue. And it does not hurt to know where 1 through 17? Oh, doesn't look like it's jumping into every single one, but a lot of them. How they work and where they work. So hit pause. Maybe write this chart down. Cannot hurt to know. Proteoglycans are large complexes of numerous polysaccharides attached to a common protein core. They strengthen bone by forming compression-resistant networks between the collagen fibrils. Proteoglycans also control the transport and distribution of electrically charged particles, particularly calcium, through the bone matrix, thereby playing a role in bone calcium deposition and calcification. Your glycoproteins. Glycoproteins are carbohydrate protein complexes of bone. Glycoproteins control the collagen interaction that lead to fibril formation. They also may play a role in calcification. Some of the glycoproteins in bone matrix include bone sialoprotein, osteocalcin, osteonectin, laminin, albumin, and alpha-glycoprotein. Other proteins found in bone matrix are the compounds currently called bone morphogenic proteins. Sialoprotein, or osteopontin, comprises about 8% of the non-collagenous matrix of bone and easily binds with calcium. Osteocalcin is also a calcium binding protein that binds preferentially to calcium that has already crystallized. The roles of osteocalcin may be to inhibit calcium phosphate precipitation and to play a part in bone resorption by recruiting osteoclasts. Osteonectin is a bone-specific protein that binds selectively to both hydroxyapatite and collagen in the bone matrix. Laminin is an abundant bone matrix protein in humans that stabilizes basement membranes in bones and is important in neurite and axon growth. Bone albumin is identical to serum albumin. In calcified matrix, bone albumin is permanently fixed to bone mineral crystals and remains so until the bone is resorbed. Bone albumin transports essential elements such as hormones, ions, and other metabolites to and from the bone cells and maintains osmotic pressure of bone fluid. Your bone minerals. After collagen synthesis and fiber formation, the final step in bone formation is the mineralization. Mineralization has two distinct phases, one being formation of hydroxyapatite crystals within matrix vesicles that bud from the surface membrane of chondrocytes, osteoblasts, and odontoblasts. And part two, the proliferation and accretion of hydroxyapatite into the extracellular matrix and its deposition between collagen fibrils. So table 44.6 lists the sequence in which calcium and phosphate form amorphous calcium phosphate compounds that are converted into stages to solid hexagonal crystals of hydroxyapatite. As the calcium and phosphorus concentrations increase in the bone matrix, the first precipitate to form is dicalcium phosphate dihydrate. Once this dicalcium phosphate dihydrate precipitation begins, the remaining phases of bone crystal formation proceed until insoluble HAP is produced, with approximately 80 to 90% of that HAP being incorporated into collagen fibers. Amorphous calcium phosphate is distributed throughout the bone matrix. So here's that table 44.6, where you see the dicalcium phosphate dehydrate, your octocalcium phosphate, your amorphous calcium phosphate, your tricalcium phosphate, and your hydroxyapatite. So if you don't know what the formulas are for, let's say, chemistry, or you don't know the abbreviations, here is a good spot to pause just to kind of give yourself a refresher. This might not be specifically, how do I put this? It might not be specifically, your pathophysiology aspect. This might be more like your biochemistry, but it doesn't hurt to know these things. And I'll be honest, I forget some of these too. So sometimes I'll just jump to the abbreviation just because I can't remember them all either. So, types of bone tissue. Bone is composed of two types of bony or osseous tissue: compact bone and spongy bone. Compact bone constitutes approximately 85% of the skeleton. Spongy bone comprises to about 15%. Both types of bone tissue contain the same structural elements, and with a few exceptions, both compact bone and spongy tissue are present in every bone. The major difference between the two types of tissue is the organization of the elements. So here you're taking a look at a bone. So if you need a quick refresher of your anatomy, pause here, read it over. Compact bone is highly organized, solid, and extremely strong. The basic structural unit is compact bone, is the Haversian system. Each Haversian system is made up of the following. And here you have the inside of a bone. Again, pause if you need a refresher of your anatomy. Nothing wrong with it. That's why the pause button exists. So your Haversian system each has these 5 steps. 1. A central canal called the Haversian canal. Part 2. Concentric layers of bone matrix called lamellae. Part 3. Tiny spaces, those lacuna between the lamellae. Step 4. Bone cells, your osteocytes within the lacunae. And then lastly, part 5. Small channels or canals called canaliculi. Each Haversian system is a separate cylindrical entity that looks like a set of concentric rings. In the center of the Haversian system is the Haversian canal that runs through the long axis of bone and contains 1 or 2 blood vessels and nerve fibers. The blood vessels in the canal communicate with blood vessels in the periosteum and marrow cavity to transport nutrients and waste to the forearm, to and from the osteocytes contained within the lacunae. Surrounding each Haversian system or canal are the concentric lamellae. Between the lamellae are the lacunae. each of which contains one osteocyte. The lacunae are connected to each other and to the Haversian canal by the canaliculi, which run parallel to the horizontal axis of the bone. Each canaliculus encloses a small extension from the osteocyte obtained in the lacuna. The canaliculi transport both nourishment and molecular signals into the lacunae, a mechanism essential for osteocyte survival. Spongy bone is less complex and lacks Haversian systems. In spongy bone, the lamellae are not arranged in concentric layers, but in plates or bars termed trabeculae that branch and unite with one another to form an irregular meshwork. The patterns of meshwork is determined by the direction of stress on the particular bone. The spaces between the trabeculae are filled with red bone marrow. The osteocyte containing lacunae are distributed between the trabeculae and interconnected by canaliculi. Capillaries pass through the marrow to nourish the osteocytes. All bones are covered with a double-layered connective tissue called the periosteum. The outer layer of the periosteum contains blood vessels and nerves, some of which penetrate to the inner structure of the bone through channels called the Volkmann canals. The inner layer of the periosteum is anchored to the bone by collagenous fibers that penetrate the bone. They're called your Sharpie fibers, and Sharpie fibers also help hold or attach tendons and ligaments to the periosteum of the bones. So characteristics of bone. The human skeleton consists of how many bones? 206. That constitute the axial skeleton and the appendicular skeleton. The axial skeleton consists of 80 bones that make up the skull, vertebral column, and thorax. The appendicular skeleton consists of 126 bones that make up the upper and lower extremities and shoulder girdle. And at the pelvic girdle, the skeleton contributes about 14% of the weight of the adult human body. So, if you really need an anatomy refresher, hit pause here and you can look at the major bones of the body. Bones can be classified by shape as long, flat, short, or irregular. Long bones are longer than they are wide and consist of a narrow tubular midportion that merges into the broader neck and a broad end. The diaphysis consists of a shaft of thick, rigid compact bone that can tolerate bending forces. Contained within the diaphysis is the elongated marrow cavity. The marrow cavity of the diaphysis contains primarily fatty tissue, which is referred to as yellow marrow. The yellow marrow assists red bone marrow in hematopoiesis only during times of stress. The yellow marrow cavity of the diaphysis is continuous with marrow cavities in the spongy bone of the metaphysis and diaphysis. The marrow contained within the epiphysis is red because it contains primarily blood-forming tissue. A layer of connective tissue, the endosteum, lines the outer surface of both types of marrow cavity. The broadness of the epiphysis allows weight bearing to be distributed over a wide area. The epiphysis is made up of spongy bone covered by a very thin layer of compact bone. In a child, the epiphysis is separated from the metaphysis by a cartilaginous growth plate, the epiphyseal plate. After puberty, the epiphyseal plate calcifies, and epiphysis and metaphysis merge. By adulthood, the line of demarcation between the epiphysis and metaphysis is undetectable. In flat bones, such as the ribs or scapula, Two plates of compact bone are roughly parallel to each other. Between the compact bone plate is a layer of spongy bone. Short bones, such as the bones of the wrist or ankle, are often cuboidal in shape. They consist of spongy bone covered by a thin layer of compact bone. Irregular bones, such as the vertebra, mandible, or other facial bones, have various shapes that include thin and thick segments. The thin of the irregular bone consists of two plates of compact bone, with spongy bone between the plates. The thick part consists of spongy bone surrounded by a layer of compact bone. So, our maintenance of bone integrity is done via remodeling. The integrity of bone is maintained by bone remodeling, a three-phase process in which existing bone is resorbed and new bone is laid down to replace it. Your osteoclasts and osteoblasts work together as a basic multicellular unit to remove old bone by osteoclast activity and to deposit new bone by osteoblast activity. The basic multicellular units are made up of bone precursor cells that differentiate into osteoclasts and osteoblasts. Precursor cells are located on the free surface of bones and along the vascular channels. In phase 1, that activation of remodeling cycle, a stimulus activates programmed osteocyte cell death. The distribution of these apoptotic osteocytes provides the osteoclasts with information about where to begin resorbing damaged bone. In phase 2, resorption, the osteoclasts form a cutting cone which gradually resorbs bone, leaving behind an elongated cavity termed a resorption cavity. Osteoclasts attach to the bone matrix by actin, microfilaments, and multiple other proteins that form foot-like structures called podosomes. Once attached, the osteoclast's integrin receptors anchor the microfilaments to the extracellular matrix, thus providing receptor pathways between the osteocyte and bone matrix. Lysosomal enzymes produced by the osteoclasts begin digesting bone, and the osteoclasts then release the degraded bone products into the vascular system. Leading us to the last step, in phase 3, the formation of new bone. Formation begins as osteoblasts lining the walls of the resorption cavity express osteoid and alkaline phosphatase, forming sites for calcium and phosphorus deposition. New bone is formed as the osteoid mineralizes. Successive layers in compact bone are laid down until the resorption cavity is reduced to a narrow Haversian canal around a blood vessel. In this way, the old Haversian systems are destroyed and new Haversian systems are formed. New trabeculae are formed in spongy bone. The formation phase can take 4 to 6 months in most humans. So that leads us to repair. The remodeling process can repair microscopic bone injuries, but gross injuries, such as a fracture and surgical wounds, heal by the same stages as soft tissue injuries, except that new bone instead of scar tissue is the final result. In bone, the stages of wound healing are as follows. You have 1. Your hematoma formation. This process occurs if vessels have been damaged, causing hemorrhage. Fibrin and platelets within the hematoma form a meshwork that is the initial framework for the healing with the help of hematopoietic growth factors, such as platelet-derived growth factor and TGF-beta. Step 2 is the procallus formation. Fibroblasts, capillary buds, and osteoblasts move into the wound to produce granulation tissue called procallus. Cartilage is formed as the precursor of bone, and types 1, 2, and 3 collagen are formed. Enzymes and growth factors, such as insulin and insulin-like growth factor, plus bone morphogenic protein and osteogenin, aid in this stage to start the healing. Part 3 is the callus formation. Osteoblasts in the procallus form membranous or woven bone. Enzymes increase the phosphate content and permit the phosphate to join with calcium to be deposited as mineral to harden the callus. And then the last portion, replacement. The basic multicellular units of the callus are replaced with lamellar bone or trabecular bone. So here we're taking a look at bone remodeling. Again, hit pause so you can take a look at all the different steps and how the formation takes off and puts back on. Step 5, remodeling. The periosteal and endosteal surfaces of the bone are remodeled to the size and shape of the bone before the injury happened. Synthesis of other types of collagen recedes in favor of type 1, which is the collagen found in bone. This final stage of healing or remodeling is vital because bone that does not or has not been remodeled does not have a good mechanical properties for weight bearing and mobility. The speed of which bone heals depends on the severity of the bone disruption, the type and amount of bone tissue that must be replaced, the blood supply and oxygen content at the site, the presence of growth and thyroid hormones, insulin, vitamin, and other nutrients, the presence of systemic disease, the effects of aging, and the effectiveness of treatment, including immobilization and the prevention of complications, such as infection. In general, however, hematoma formation occurs within hours of fracture or surgery. Formation of procallus by osteoblasts occurs within a few days. Callus formation occurs within a few weeks, and replacement and contour remodeling occur within years. It can take up to 4 years in some cases. So, structure and function. The site where two or more bones meet is called a joint, not the fun kind. The primary function of joints is to provide stability and mobility to the skeleton. Whether a joint provides stability or mobility depends on the location and its structure. Generally, joints that stabilize the skeleton have a simpler structure than those that enable movement of the skeleton. Most joints provide stability and mobility in some degree. So here we're taking a look at the main tissue of the joint. So just a fresh little anatomy refresher. And some more anatomy types of joints. So if you need a little anatomy refresher, here's a good spot to pause. Joints are classified based on the degree of movement they permit, or on the connecting tissue that holds them together. Based on movement, a joint is classified as a synarthrosis, an amphiarthrosis, or a diarthrosis. On the basis of the connective structures, joints are classified broadly as fibrous, cartilaginous, and synovial. Each of these three structural classifications can be subdivided according to the shape and contour of the articulating surface of the bones and the type of motion that they permit. So, talking about fibrous joints. A joint in which bone is united directly to bone by fibrous connective tissue is called a fibrous joint. Generally, fibrous joints are synarthrosis or immovable, but many fibrous joints allow some movement. The degree of movement depends on the distance between the bone and the flexibility of the fibrous connective tissue. Fibrous joints are further subdivided into three types: sutures, syndesmosis, and gomphosis. A suture has a thin layer of dense fibrous tissue that binds together interlocking flat bones in the skulls of young children. Sutures form an extremely tight union that permits no motion. By adulthood, the fibrous tissue has been replaced by bone. A syndesmosis is a joint in which the two bony surfaces are united by a ligament or membrane. The fibers of ligament are flexible and stretch, permitting a limited amount of movement. The paired bone of the lower arm and the lower leg and their ligaments are syndesmotic joints. A gomphosis is a special type of fibrous joint in which a conical projections fits into the complementary socket and is held there by a ligament. The teeth held in the maxilla or mandible are gomphosis joints. For example, your cartilaginous joints. These two types of cartilaginous joints are symphysis and synchondrosis. A symphysis is a cartilaginous joint in which bones are united by a pad or disc of fibrocartilage. A thin layer of hyaline cartilage usually covers the articulating surface of the two bones, and a thick pad of fibrocartilage acts as a shock absorber and stabilizer. Examples of symphysis are the symphysis pubis, which joins the two pubic bones, and the intervertebral disc, which join the bodies of the vertebrae. A synchondrosis is a joint in which hyaline cartilage, rather than fibrocartilage, connects the two bones. The joints between the ribs and the sternum are synchondrosis. The hyaline cartilage of these joints is called costal cartilage. Slight movement at the synchondrosis between the ribs and the sternum allows the chest to move outward and upward during breathing. Synovial joints. Synovial joints are the most movable and the most complex joints in the body. A synovial joint consists of the following parts: a fibrous joint capsule, a synovial membrane that lines the inner surface of the joint capsule, a joint cavity, a space formed by the capsule, synovial fluid, which fills the joint cavity and lubricates the joint surface, and the articular cartilage, which covers and pads the articulating bony surface. I'm going to go up here for just a moment. Hit pause here so you can take a look at this knee joint. Again, it doesn't hurt to hit pause. Do a quick 1, 2, 3 as a refresher for your anatomy. Your joint capsule. The fibrous joint capsule is connective tissue that covers the ends of the bones where they meet in the joint. Your Sharpie fibers firmly attach the proximal and distal capsules to the periosteum and ligaments and tendons, which also reinforce the capsule. The joint capsule consists of parallel interlacing bundles of dense, white fibrous tissue. It is richly supplied with nerves, blood vessels, and lymphatic vessels. The nerves in and around the joint capsule are sensitive to the rate and direction of motion, compression, tension, vibration, and pain. Synovial membrane. The synovial membrane is the smooth, delicate inner lining of the joint capsule. It lines the non-articular portion of the synovial joint and any ligaments or tendons that traverse the joint cavity. It is made up of two layers, a vascular layer and the thin cellular layer. The vascular subintima merges with the fibrous joint capsule and is composed of loose fibrous connective tissue, elastin fibers, fat cells, fibroblasts, macrophages, and mast cells. The intima consists of rows of synovial cells embedded in a fiber-free intercellular matrix. The intima contains two types of synovial cells, type A and B. Type A synovial cells ingest and remove bacteria and particles of debris by phagocytosis in the joint cavity. Type B synovial cells secrete hyaluronate, a binding agent that gives synovial fluid its viscous quality. The synovial membrane is richly supplied with blood and lymphatic vessels. Therefore, it is capable of rapid repair and regeneration. So, here is a picture of the synovium. Again, good spot, hit pause, take a look, do a quick refresher. Your joint cavity. The joint cavity is an enclosed fluid-filled space between the articulating surface of the two bones. This small cavity, often called the joint space, enables the two bones to move against one another. The synovial cavity is surrounded by the synovial membrane and is filled with a clear, viscous, slick fluid called the synovial fluid. Synovial fluid. Synovial fluid is superfiltrated plasma from the blood vessels in the synovial membrane. Synovial fluid lubricates the joint surfaces, nourishes the pad of the articular cartilage that covers the end of the bones, and contains free-floating synovial cells and various leukocytes and phagocytes, joint debris, and microorganisms. Loss of synovial fluid leads to rapid deterioration of articular cartilage. Your articular cartilage is a layer of hyaline cartilage that covers the end of each bone. It's anywhere from 2 to 5 millimeters thick, depending on the size of the joint, the fit of the two bone ends, and the amount of weight and shearing force the joint normally withstands. Cartilage strength and its biologic properties are due to an extensive network of cross-linked collagen fibers. Figure 44.12 illustrates how collagen cross-linked from cartilage. The function of articular cartilage is to reduce friction in the joint and to distribute the forces of weight bearing. Articular cartilage is composed of chondrocytes and an intracellular matrix made up of collagen, protein polysaccharides, and water. The water content ranges anywhere from 60 to 80% of the net weight of the cartilage, and individual molecules rapidly enter or exit the articular cartilage to contribute to the resiliency of the tissue. So here you see the collagen zones, the reserve, your proliferative, your hypertrophic, all the way to the bone. And here you see collagen 11, 2, and 9 interwoven together. Your heterotypic collagen fibril. The intercellular matrix is produced by the chondrocytes, which synthesize and extrude collagen that, like the collagen produced by bone cells, is distributed throughout the cartilage in a highly organized system of fibers. Collagen fibers in cartilage are made up of many fine fibrils that, like bone fibrils, are assembled in an orderly fashion that make them resistant to physical, metabolic, or chemical breakdown. The main differences between bone collagen and cartilage collagen are the amino acid content and the alpha chains, and the composition of the fibrils. Bone collagen fibrils are made up of two types of one chains and one type of two chain. Roughly 90% of the cartilage collagen fibrils are made up of three identical type 2 chains, with the remaining 10% consisting of types 5, 6, 9, 10, and 11. At the surface of articular cartilage, the collagen fibers run parallel to the joint surface and are closely compacted into a dense protective mat. In the middle layer of the cartilage, the fibers are arranged tangential to the surface, which allows them to deform and absorb some of the force of weight bearing. In the bottom layer of the cartilage, the fibers are perpendicular to the joint surface, allowing them to resist shear forces, and are embedded in the calcified layer of cartilage, called the tide mark. The tide mark anchors the collagen fibers to the underlying bone and represents the zone between calcified and non-calcified cartilage. Collagen fibers are important components of cartilage matrix because they account for approximately 60% of the dry weight, and because they 1. Anchor the cartilage securely to the underlying bone, 2. Provide a taut framework of cartilage, 3. Control the loss of fluid from the cartilage, and 4. Prevent the escape of protein polysaccharides from the cartilage. The proteoglycans are the macromolecules consisting of proteins, carbohydrates, and hyaluronic acid. One subgroup of proteoglycans, known as the heparan sulfate proteoglycans, binds to many proteins involved in musculoskeletal development and homeostasis, including FGF, BMPs, WNTs, chemokines, interleukins, and extracellular matrix proteins. The glycose aminoglycans are attached to the protein core, and several protein cores are bound to a hyaluronic acid chain by a special protein called link protein. The proteoglycans give articular cartilage its stiff quality and regulate the movement of synovial fluid through the cartilage. Without proteoglycans, normal weight bearing would rapidly and completely press all the synovial fluid out of the cartilage. Proteoglycans act as a pump, permitting enough fluid to be pressed out to ensure that the fluid film is always present on the surface of the cartilage. Even after hours of weight bearing, the pumping action of proteoglycans also draws synovial fluid back into the cartilage after a weight-bearing load is released. Mobility and weight bearing are necessary for the pumping action of proteoglycans to occur. Non-use of a joint quickly reduces the pumping action, which changes the composition of the matrix and interferes with the nutrition of the chondrocytes. Normal articular cartilage has no blood vessels, lymph vessels, or nerves. Therefore, it is insensitive to pain and regenerates slowly and minimally after an injury. Regeneration occurs primarily at sites where the articular cartilage meets the synovial membrane, where blood vessels and nutrients are available. In general, it has been difficult to enhance cartilage repair, but that may be changing. Progress in rebuilding cartilage. Although much research is needed, recent evidence suggests that mesenchymal stem cell therapies may be a potential solution to rebuilding articular cartilage. Multipotent adult stem cells are largely available and accessible. It is theorized that bone marrow mesenchymal stem cells secrete proliferative and regenerative factors in the lesion sites of articular cartilage, thereby retarding osteoarthritis progression and promoting articular cartilage regeneration locally by trophic effects. Gene therapy also represents a novel approach to managing joint degradation. The principle of gene therapy is the overexpression of desired gene products. Gene therapy can support articular cartilage generation by targeting different genes involved in different cellular processes, such as inhibiting inflammatory and catabolic pathways, stimulating anabolic pathways, or preventing cell senescence and apoptosis. Candidate transgene studies are currently in the exploratory phases, generally using animal models. Candidate transgenes with anti-inflammatory action include interleukin-1 receptor antagonists and soluble tumor necrosis factor. Gene therapy strategies also may target the catabolic effects of matrix metalloproteinases by the delivery of tissue inhibitor of metalloproteinases. The overexpression of growth factor has been shown to enhance matrix formation. TGF beta, in particular, was reported to aid cartilage regeneration and enhance meniscal tissue healing in vitro. GT shows promise for the future, however, to ensure safety and efficacy through evaluation of the technique as necessary. Your movement. Synovial joints are described as uniaxial, biaxial, and multiaxial according to the shapes of the bone ends and the types of movement occurring at the joint. Usually, one of the bones is stable and serves as an axis for the motion of the bone. The body movement made possible by various synovial joints are either circular or angular. So here we're taking a look at your uniaxial and biaxial, the movements of synovial joints, and your multiaxial. Pardon me. Structures and function of skeletal muscle. Skeletal muscles arise from the mesodermal progenitor cells. The most numerous are the somites. Actual formation of skeletal muscle is a complex process controlled by multiple signaling factors. A critical component of successful embryonic muscle formation is protein kinase, an enzyme that adds phosphate groups to substrate proteins, thereby directing cell processes. In muscles, these factors direct formation of myoblasts. Once the myoblasts are formed, they fuse with other myoblasts and form myotubes, eventually developing into muscle fibers. At birth, the muscle fibers have completed development from myoblasts. Final muscle types is determined by transcription factors that regulate both pre and postnatal muscle development. All voluntary muscles are derived from the mesodermal layer of the embryo. Genetic transcription factors, most notably myoblast determination protein, induce skeletal muscle differentiation. Myoblasts are the main cells responsible for muscle growth and regeneration. Myoblasts are termed satellite cells when in a dormant state and are crucial in muscle growth, maintenance, repair, and regeneration. Once muscle is injured, satellite cells become activated and increase the number of transcriptional factors necessary to form myoblasts and assist in repair. Skeletal muscles are made up of millions of individual fibers that, by processes of contraction and relaxation, do the work necessary to complete movements as varied as a ballerina's pirouette or an artist's deft stroke. Muscle constitutes 40% of adults' body weight and 50% of children's body weight. Muscle is 75% water, 20% protein, and 5% organic and inorganic compounds. 32% of all protein stores for energy and metabolism is contained in the muscles. So, for those who really struggled with anatomy, here is a good time to pause and get that refresher of all your muscle groups. Whole muscles. There's more than 350 named muscles. Almost all are paired. The body's muscles vary dramatically. They range from 2 to 60 centimeters in length and are shaped according to the function. Fusiform muscles are elongated muscles, shaped like straps and can run from one joint to another. Your pennate muscles are broad, flat, and slightly fan-shaped, with fibers running obliquely to the muscle's long axis. The multipennate deltoid muscle, which flexes and extends the arm, is a good example of a muscle shaped according to its function. Each skeletal muscle is a separate organ encased in a three-part connective tissue framework called fascia. The layers of connective tissue protect the muscle fibers, attach the muscle to bony prominences, and provide a structure for a network of nerve fibers, blood vessels, and lymphatic channels. The outermost layer, the epimysium, mycelium, is located on the surface of the muscle and tapers at each end to form the tendon. Tendons allow a short muscle to exert power on a distant joint, whereas thick muscle interferes with joint mobility. The next layer, the perimysium, further subdivides the muscle fibers into bundles of connective tissue, or fascicles. The endomysium surrounds the muscle fascicles, the smallest unit of muscle fibers visible without a microscope. The ligaments, tendons, and fascia are made up of connective tissue that also serves to buffer the limbs from the effects of sudden strains or changes in speed. The rapid recovery necessary for strenuous exercise is supported by the elastic properties of muscle and its connective tissue. Skeletal muscle is described almost interchangeably as voluntary striated or extrafusal. Voluntary indicates that the muscle is controlled directly by the central nervous system. Striated describes the striated or striped pattern of skeletal muscle viewed under the light microscope. The striations results from the organization of the muscle fibers into the contractile units called sarcomeres. Extrafusal distinguishes the skeletal muscle fibers from other contractile fibers located within the sensory organ of the muscles. Other components that are visible on gross inspection of the whole muscle include the motor and sensory nerve fibers. These functions together with the muscle, innervating portions of it and providing the electrical impulses needed for motor function. The motor unit. From the anterior horn cell of the spinal cord, the axons of the motor nerve branch out to innervate a specific group of muscle fibers. Each anterior horn cell, its axon, and the muscle fibers innervated by it are called a motor unit. The motor units are composed of lower motor neurons, which extend to skeletal muscles, often termed the functional unit of the neuromuscular system. The motor unit behaves as a single entity and contracts as a whole when it receives an electrical impulse. So here you see how the motor unit works with the skeletal muscle. Or, I'm sorry, the skeletal body and the muscle fibers. The whole muscle may be controlled by several motor nerve axons. These branch out to innervate many motor units within the muscle. The whole muscle then may consist of many motor units. The number of motor units per individual muscle varies greatly. In the calf, for example, one motor axon will innervate approximately 2,000 muscle fibers out of the total 1,200,000 muscle fibers. This is a high innervation ratio of muscle fibers to axons, and it contrasts markedly with the low innervation ratio in the laryngeal muscles, where 2 or 3 muscle fibers constitute each motor unit, and the innervation ratio can be of great functional significance. The greater the innervation ratio of the particular organ, the greater its endurance. The higher innervation ratio prevents fatigue and lower innervation ratios allows for precision of movement, leading us to our sensory receptors. Although muscle function as effector organs, they also contain sensory receptors and are involved in sending different signals to central nervous systems. Among these are the muscle spindles and the Golgi tendon organs. Spindles are mechanoreceptors that lie parallel to muscle fibers and respond to muscle stretching. Golgi tendon organs are dendrites that terminate and branch to tendons near the neuromuscular junction. Motor and sensory neurons secrete a proteoglycan called neuralgin that increase the number of acetylcholine receptors and help in the formation of muscle spindle fibers. Muscle spindles, Golgi tendon organs, and free nerve endings provide a means of reporting changes in length, tension, velocity, and tone in the muscles. This system of afferent signals is responsible for the muscle stretch response and maintenance of normal muscle tone. Muscle fibers. Each muscle fiber is a single muscle cell. This long cell is cylindrical and surrounded by a membrane capable of excitation and impulse propagation. The muscle fiber contains bundles of myofibrils, the fiber's functional subunits, in a parallel arrangement along the longitudinal axis of the muscle. At birth, the muscle fibers have complete development from precursor cells called myoblasts. All voluntary muscles are derived from the mesodermal layer of the embryo. So here we're taking a look at myofibrils of the skeletal muscle fiber. Again, not a bad spot to stop and do a quick refresher for your anatomy. The type of peripheral nerve influences the muscle fibers and motor unit considerably. That is, the type of muscle fiber in the motor unit is determined by whether the motor nerve is a fast or slow one. Type 2 fibers are also called white fast motor fibers, are innervated by relatively large type 2 alpha motor neurons with fast conduction velocities. These fibers rely on a short-term anaerobic glycolytic system for rapid energy transfer, whereas type 1 fibers depend on aerobic oxidative metabolism. Histochemical stains are now routinely used to describe the structure of muscle fibers and contractile elements of muscle biopsy specimens. Muscle fiber type 2 fibers stains dark with the enzyme stain ATPase at a pH of 9.4. Red muscle type 1 fibers appears lightly stained. The overlap of muscle fibers that appear with staining gives the checkerboard appearance of muscle biopsy specimens and provides an equal distribution of fiber types throughout the muscle. This overlap also helps compensate for muscle fiber loss and fatigue of individual motor units during activity. In spite of this, some muscles contain proportionately more of one fiber type than another. The postural muscles have more type 1 fibers, allowing them the high resistance to fatigue that is necessary to maintain the same position for extended periods. Ocular muscles have more type 2 muscle fibers, allowing them to respond rapidly to visual changes. So here we have the characteristics of muscle fibers. The characteristic, the type 1 or type 2. So not a bad spot to do a quick pause and take a quick anatomy and physiology review. The number of muscle fibers varies according to location. Large muscles, such as the gastrocnemius, I think they misspelled that, have more fibers than smaller muscles, such as the lumbrical muscles in the hand. The diameter of muscle fibers also varies. The closely packed polygons are small until puberty, and when they attain the normal adult diameter, 40 to 80, women usually have smaller diameter fibers than men. Small muscles, such as the ocular muscles, are only 15 in diameter. Larger, more proximal muscles are 40 in diameter. Both fibers, or both fiber size and muscle length, have functional significance. Studies have shown that larger fiber diameter is associated with generation of greater forces. Fiber diameter can be increased by activities that cause hypertrophied muscles, such as exercise or occupational overuse. The major components of the muscle fiber include the muscle membrane, myofibrils, sacrotubular system, sarcoplasm, and mitochondria. The muscle membrane is a two-part membrane. It includes the sarcolemma, which contains the plasma membrane of the muscle cell, and the cell's basement membrane. The sarcolemma is 7.5 thick and is capable of propagating electrical impulses to initiate contraction. At the motor nerve end plate, where the nerve impulse is transmitted, the sarcolemma forms the highly convoluted synaptic cleft. The sarcolemma is comprised of lipid molecules and protein systems. The protein system performs special functions, such as the transport of nutrients and synthesis of proteins. They also provide the sodium-potassium pump and include the cell's cholinergic receptor. The basement membrane is 50 thick and is composed primarily of proteins and polysaccharides. It serves as the cell's microskeleton and maintains the shape of the muscle. The basement membrane also may function in some way to restrict further diffusion of electrolytes once they have crossed the sarcolemma. The sarcoplasm is the cytoplasm of muscle cells and contains the intracellular components that are common to all cells. The sarcoplasm is an aqueous substance that provides a matrix that surrounds the myofibrils. It contains numerous enzymes and proteins that are responsible for the cell's energy production, protein synthesis, and oxygen storage. The mitochondria house enzyme systems for energy production, particularly those that regulate such processes as citric acid cycle and adenosine triphosphate formation. Many other structures are present in the sarcoplasm. The ribosomes are composed primarily of RNA and participate in the process of protein synthesis. The cell nucleus, satellite cells, glycogen granules, and lipid droplets are suspended in the sarcoplasmic matrix. Blood vessels, nerve endings, muscle spindles, and Golgi tendon organs are also directly located within this structure. Unique to the muscle is the sarcotubular system, a network that includes the transverse tubules and the sarcoplasmic reticulum, which crosses the interior of the cell. The sarcoplasmic reticulum is made of the same manner as the endoplasmic reticulum in other cells. In the muscle cells, the sarcoplasmic reticulum is involved in calcium transport, which initiates muscle contraction at the sarcomere, a portion of the myofibril. The sarcoplasmic reticulum is composed of tubules that run parallel to the myofibrils. The longitudinal tubules are termed sarcotubules. The transverse tubules, which are closely associated with the sarcotubules, run across the sarcoplasm and communicate with the extracellular space. Together, the tubules of this membrane system allows for intracellular calcium uptake, regulation, and release during muscle contraction, and for the storage of calcium during muscle relaxation. Your myofibrils. Myofibrils, the most abundant subcellular muscle component, are the functional units of muscle contraction. Each myofibril contains sarcomeres, which in turn consist of repeating protein filaments. Sarcomeres are chiefly composed of the proteins actin, myosin, titin, and nebulin. The sarcomere is responsible for converting chemical energy into movement. On cross-section, they are irregular polygons with a mean diameter of less than 1 UM. Each myofibril is composed of serially repeating sarcomeres, separated by Z-lines that give the muscle its striped, cross-striated appearance. Each sarcomere has a dark A band and is flanked by two light I bands. Titin functions as a molecular spring that plays a significant role in determining muscle stiffness and elasticity. The A band is 1.5 to 1.6 long and contains thick myosin filaments. Included in the A band is a lighter zone called the H band, and in the center of the H band is that dark M band or M line. The I band, which contains actin, is divided at the midpoint of each sarcomere by the Z line. Its length varies with the start of the muscle contraction. Again, this is your anatomy review. A good spot to hit pause to take a physical look of the different locations of I band, H band, M line, A band, and how titin, actin all work together on your muscle fibers. Myofibrils are composed of myofilaments. Each myofilament is structured in a closely packed hexagonal arrangement with two thin filaments for each thick filament. The thick filament, along with C protein and M-line protein, is made up of myosin. Myosin has two subunits, heavy and light myromyosin, which resemble twisted golf club shafts. The thin filaments are twisted double strands made up of actin, troponin, and tropomyosin. Your muscle proteins. The following table summarizes muscle protein distribution, location, and possible function significance. The contractile and regulatory functions of actin, myosin, and the troponin-tropomyosin complex are the most commonly known. They also account for most of the protein found in the myofibril. The structural and regulatory processes of muscle proteins are less well understood. Alpha-actin and beta-actin are known to link the filaments. M protein contains the enzyme creatinin kinase. Creatinine is released when muscle cells are damaged, making the serum creatinine value an important measurement of pathologic conditions of muscles. So here you see the contractile proteins of the skeletal muscles. Sounds like a good spot to hit pause. And here's the end of it. The most abundant proteins, actin and myosin, are also found in other cells, particularly motile cells, such as platelets. The complete amino acid sequence of actin and myosin have been identified. Noteworthy is the presence of the amino acid 3-methylhistidine, found only in the thin filament actin. 85 to 90% of 3-methylhistidine is found in the skeletal muscle. The amino acid lysine and histidine is, in addition to leucine, have been used to study protein synthesis by means of stable isotope infusion and muscle biopsy analysis. Your non-protein constituents of muscle. So, your nitrogen, creatinine, creatine, phosphocreatine, purines, uric acid, and amino acids serve in the complex process of muscle metabolism. Phosphocreatine concentration is an extremely sensitive indicator of muscle fiber activity. Glycogen and its derivatives are present as energy sources. Creatine metabolism and creatinine metabolism have been used to measure muscle mass. Plasma creatine is taken up by muscles and converted into a high-energy phosphate compound, creatine by the enzyme creatine kinase. Creatinine is formed in muscles from creatine at a constant rate of 2% per day. Creatine excretion is increased in muscle wasting. This change reflects the reduction in total body creatine stores and loss of muscle mass. Inorganic compounds, anions, and cations are important in regulating protein synthesis, muscle contraction, enzyme systems, and membrane stabilization. Intracellular calcium levels influence the force and duration of muscle contraction. Total body potassium level, measured by the potassium method, has been used to measure muscle mass, also called lean body mass. Your total body potassium levels reflect changes in muscle mass seen during growth, malnutrition, and muscle wasting. Components of muscle function. The ultimate function of muscle is to accomplish work. Although variously expressed in such measures as foot-pounds or kilogram-meters, work usually refers to the amount of energy liberated or force exerted over a distance. Muscles usually contract or tense while doing work. Muscle contraction occurs on the molecular level and leads to the observable phenomenon of muscle movement. Muscle contraction at the molecular level. Muscle contraction is a four-step process: excitation, coupling, contraction, and relaxation. The initial contraction process is the excitation-contraction coupling series, which involves the electrical properties of all cells and their movements of ions across the plasma membrane. At rest, an electrical charge of 90 millivolts is continually maintained across the muscle sarcolemma. This resting potential, generated by the separation of positive and negative charges on either side of the membrane, create an electrochemical equilibrium caused by the selective permeability of the sarcolemma to electrolytes in the intracellular and extracellular fluids, particularly potassium and sodium. Specific intracellular receptors within the skeletal muscle sarcoplasmic reticulum, called ryanodine receptors, are the primary ion channels that control calcium release. Your ryanodine receptors are the largest known ion channels, allowing for rapid movement of calcium. 3 ryanodine receptors have been identified. Type 1 is predominantly found in skeletal muscle. Type 2 is found mostly in cardiac muscle, and type 3 is found in the diaphragm, smooth muscle, and brain. Excitation is the first step of muscle contraction. Begins with the spread of an action potential from the nerve terminal to the neuromuscular junction. The rapid depolarization of the membrane initiates the electrical impulse in the muscle fiber membranes, called the muscle fiber action potential. As the action potential advances along the sarcolemmal membrane, it spreads to the transverse tubules. The generated action potential then triggers a voltage-sensitive receptors in the T-tubule wall. In turn, these receptors open the RYR channels, causing release of calcium from the sarcoplasmic reticulum. Following depolarization of the T-tubules, the second stage, the coupling, occurs. This stage consists of the migration of calcium ions to the myofilaments. Calcium affects troponin and tropomyosin, muscle proteins, that bind with actin when the muscle is at rest.
In the presence of calcium, however, both of these proteins are attracted to calcium ions, leaving the free actin to bind with myosin. Contraction begins as the calcium ions combine with troponin, a reaction that overcomes the inhibitory function of the troponin-tropomyosin system. The thin filament actin then slides towards the thick filament myosin. The two ends of the myofibril shorten after contraction when the myosin heads attach to the actin molecules, forming a cross bridge that constitutes an actin-myosin complex. ATP, located on the actin-myosin complex, is released when the cross bridges attach. This is the sliding filament theory and was first described by A. F. Huxley in the 1950s. However, it is now called the cross-bridge theory because of the formation of the actin-myosin cross bridges. The process is so named because the actin actually slides onto the myosin, causing the sarcomere to shorten. The useful distance of contraction of the skeletal muscle is approximately 25% to 35% of the muscle's length. When actin and myosin filaments have maximal interaction, the muscle generates maximal force. The last step, relaxation, begins as the sarcoplasmic reticulum absorbs the calcium molecules, removing them from interaction with troponin. Calcium is pumped back into the sarcoplasmic reticulum by means of an active transport process. The cross bridges detach and the sarcomere lengthen. So muscle metabolism. Skeletal muscle requires a constant supply of ATP and phosphocreatine. These substances are necessary to fuel the complex processes of muscle contraction, driving the cross bridges of actin and myosin together and transporting calcium from the sarcoplasmic reticulum to the myofibril. Other internal processes of the muscular system that require ATP include protein synthesis, which replenishes muscle constituents and accommodates growth and repair. The rate of protein synthesis is related to hormone levels, amino acid substrates, and overall nutritional status. At rest, the rate of ATP formation by oxidation of glucose and acetoacetate is sufficient to maintain internal processes. Given normal nutritional status, during activity the need for ATP increases 100-fold. The metabolic pathway for muscle activity in Table 44.9 shows reactions to the immediate need for increased ATP caused by contraction. Activity lasting longer than 5 seconds expends the available stored ATP and phosphocreatine. So here we see the energy sources for muscular activity. Short versus long term. Stored glycogen and blood glucose are converted anaerobically to sustain brief activity without increasing the demand for oxygen. Anaerobic glycolysis is much less efficient than aerobic glycolysis, using 6 to 8 times more glycogen to produce the same amount of ATP. With increased activity, such as intense exercise or ischemia, an increase in the level of lactic acid occurs because of the breakdown of glycogen, thus causing a shift in muscle pH. This short-term mechanism buys time by allowing ATP formation in spite of inadequate energy stores or oxygen supply. When the anaerobic threshold is reached and more oxygen is required, physiologic changes occur, including an increase in lactic acid concentration and increases in oxygen consumption, heart rate, respiratory rate, and muscle blood flow. Strenuous exercise requires oxygen, which activates the aerobic glycogen pathway for ATP formation. During maximal exercise, free fatty acid mobilization and the aerobic glycogen pathways provide ATP over an extended time. These pathways require oxygen to maintain maximal activity and return the muscle to the resting state. Maximal exercise increases oxygen uptake 15 to 30 times over the resting state. When the system becomes exhausted or unable to respond to the need for ATP, fatigue and weakness finally force the muscle to reduce activity, with a resultant buildup of lactic acid in the muscle fibers. The ability to sustain maximal muscular activity leads to the accumulation of oxygen debt. Oxygen debt is the amount of oxygen needed to convert the buildup of lactic acid to glucose and replenish ATP and phosphocreatine stores. For example, after running at maximal speed for 10 seconds, the average person has consumed 1 liter of oxygen. At rest, oxygen consumption for the same period is approximately 40 milliliters. As the person recovers, the measured oxygen depth is 4 liters greater than the amount used during activity. Oxygen consumption is measured to calculate the metabolic cost of activity in normal and diseased muscle. It is an indirect measurement of energy expenditure along with time tests or activity, heart rate, and respiratory quotient. Energy expenditure is measured directly by heat production because heat is released whenever work is accomplished. Another factor changes energy requirements in muscle fiber type. Type 2 fibers rely on anaerobic glycolytic metabolism and fatigue readily. Type 1 fibers can resist fatigue for long periods because of their capacity for oxidative metabolism. So, muscle mechanics. The muscle contraction cannot be viewed in isolation. Several factors determine how force is transmitted from the cross bridges on the individual muscle fibers to accomplish whole muscle contraction. First, when a motor unit responds to a single nerve stimulus, it develops a phase contraction, also called twitch, because the motor unit contracts in an all or nothing manner. The contraction that is generated will be a maximal contraction. The central nervous system smoothly grades the force generated by recruiting additional motor units and varying the discharge frequency of each motor unit. This adding of motor units within the muscle is called repetitive discharge. Recruitment and repetition Recruitment and repetitive discharge of motor units allow the muscle to activate the number of motor units needed to generate the desired force. The total force developed is the sum of the force generated by each motor unit. As the strength, speed, and duration of stimuli increase, the summation of contraction reaches a critical frequency called tetanus. When tetanus is reached, no further increase in force can be achieved. Other variables, such as the fiber type, innervation ratio, muscle temperature, and muscle shape, influence the efficiency of muscular contraction. The two muscle fiber types differ in their response to electrical activity. Tetanus and duration of phasic contraction, which take microseconds to accomplish, are achieved more rapidly in type 2 than in type 1 muscle fibers. Low innervation ratios promote control and coordination, whereas high ratios promote strength and endurance. Muscle work best at normal body temperature. Muscles work best at normal body temperature. Finally, muscles with a large cross-sectional area, such as the fan-shaped pennate muscles, develop greater contractile force than smaller diameter muscles. The initial length of the muscle and the range of shortening that occur when the muscle contracts also determines the force it can generate. The long fusiform muscles have a great range of shortening and can contract up to 57% of their resting length. A certain amount of elongation is necessary to generate sufficient tension and muscular force. The elongation that occurs during the swing of a golf club or tennis racket is an example of how stretch improves contractile force. Types of muscle contraction. During isometric contraction, the muscle maintains constant length as tension is increased. Isometric contraction occurs, for example, when the arm or leg is pushed against an immovable object. The muscle contracts, but the limb does not move. During dynamic contraction, formerly known as isotonic contraction, the muscle maintains a constant tension as it moves. The term eccentric for lengthening and concentric for shortening are technically inaccurate descriptions of muscle movement. The respective terms lengthening and shortening are more precise. Positive work is accomplished during shortening, and energy is released to exert force or lift a weight. In contrast, during lengthening, the muscle lengthens and absorbs energy. Negative work is accomplished on the muscle by the load. Lengthening requires less energy to accomplish and may result in the development of pain and stiffness after unaccustomed exercise. Movement of muscle groups. Muscles do not act alone, but rather in groups, often under automatic control. When a muscle contracts, it acts as a prime mover or agonist, and its reciprocal muscle or antagonist relaxes. This is easily tested by holding the right arm in the horizontal position in front of the body and then bending the elbow while feeling the upper arm, the bicep, in the front and the tricep in the back. With the other hand, the bicep is firm and the tricep is soft. As the arm is extended, the muscles change. When the elbow is completely extended, the bicep is soft and the tricep is firm. Completing this movement causes the agonist and antagonist to change automatically. Only the movement is commanded, not the alternate contraction and relaxation of the specific muscle groups. Other associated actions may be seen during walking. As the foot leaves the ground, the paravertebral and gluteal muscles on the opposite side of the body contract to maintain balance. One notices the loss of the associated muscles action when paralysis offsets this process and decreases balance. If a person is paralyzed, difficulty in maintaining balance is noticeable. So tests of musculoskeletal function, tests of bone function. Diagnostic procedures to evaluate bone function include gait analysis, measurements of serum calcium and phosphorus levels, and imaging studies. Most imaging techniques provide morphologic rather than functional information about bone. Plain radiograph remain the standard initial imaging tool for bone evaluation because bone absorbs X-ray beams better than soft tissue. CT provides multiple images that are then processed into single or multiple images taken around a single axis to form pictures. Dual energy computed tomography utilizes X-ray beams at two different energy levels to determine different chemical compositions of tissue, thereby expanding CT images to include soft tissue, bone marrow, and crystals. Advances in CT technology allows for detailed visualization and bone microstructure. MRI provides detailed anatomic information and is useful for evaluating primary or metastatic bone lesions, infections, marrow edema, bony erosion, osteonecrosis, fractures, and other pathologic changes of bone.
Your MRA involves injection of a contrast agent into the area of interest, but allows better visualization of small abnormalities. Detailed functional imaging of bone can be attained with positron emission tomography scanning. A relatively new technology, MRI PET, combines MRI with functional imaging of molecular events seen with PET scans. Nuclear medicine studies also provide imaging about metabolic activity in bone and soft tissue. After a small amount of radioactive tracer is injected, a special camera is used to identify bone absorption of the tracer. Bone scanning is very sensitive, but not specific, about the cause of increased metabolic activity. Your dual photon absorptiometry is often used to measure the density of bones in the extremities and the fracture risk of vertebral bodies, femoral neck, and distal radius. Dual photon absorptiometry allows the soft tissue components to be subtracted. New technology promises more accurate evaluation of bone. Serum bone specific alkaline phosphatase is a marker of bone formation. Bone resorption is evaluated with urinary and serum measurements of cross-linked N-terminal telopeptides, a product of osteoclast bone resorption. NTX is specific for bone because the crosslinks assessed are characteristic of bone collagen alone. Urine NTX is a more sensitive and specific biochemical marker of bone resorption than serum NTX. So tests of joint function. Procedures used to diagnose joint function include arthrography, arthroscopy, MRI, and synovial fluid analysis. Arthrography is particularly useful to diagnose tears in the fibrocartilage of the knee and the rotator cuff of the shoulder. Arthroscopy is the direct visualization of the joint through an arthroscope. MRI produces images of body tissue through the use of electromagnetic waves that alter the atoms in the nuclei of cells being examined. When the polarized radio waves are stopped, the nuclear atoms return to their original position, emitting energy as signals as they move back. The signals produce visible images for examination and diagnosis. MRI produces excellent contrast of soft tissue for evaluation of musculoskeletal conditions. MRAs is injection of contrast into the joint, followed by an MRI evaluation. Analysis of synovial fluid may reveal inflammatory, septic, and non-inflammatory joint disease, which cause characteristic changes in the color, clarity, viscosity, and cellular elements of the fluid. The presence of blood in the joint usually indicates joint trauma. Normal synovial fluid is sterile, so the presence of bacteria in the fluid always indicates disease. Cell fragments and fibrous tissue in the fluid are the result of inflammation or wear and tear on the articular surface. Tests of muscular function. When the individual's history and physical exam disclose abnormalities, such as weakness, atrophy, muscle tenderness, cramps, and stiffness, specific tests of muscle function are in order. One of the most useful tests is your serum creatinine kinase concentration. CK is found in large quantities in muscle fibers, and when these fibers are diseased or damaged, CK leaks into the serum. Myoglobin is also detectable in the urine after acute muscle damage caused by crush injuries, ischemic disorders, extreme exertion, and some inherited diseases. Because the muscle membrane tissue is excitable and carries an electrical charge, its capacity to function can be assessed by electromyography. Using sensitive needle electrodes, the electromyogram records the summation of action potentials of the muscle fibers in each motor unit. The EMG is often compared with EKGs but the activity recorded on the EMG is on a much smaller scale. The amplitude of the EKG is measured in volts. The duration of impulse is recorded in seconds, and both are recorded as the heart rate. EMG amplitude is recorded in millivolts, and the duration is measured in milliseconds, with a frequency of about 5 to 50 action potentials per second. Motor unit potentials are measured to determine rate of fire, duration, and amplitude. Abnormalities in EMG and nerve conduction velocities help differentiate muscle disease from peripheral nerve and neuromuscular junction disorders. The muscle biopsy is used to further define the presence of myopathic and neuropathic disorders, many of which can be diagnosed only by muscle biopsy. Complex myography, a relatively new technique, allows a non-invasive way to gather information on the mechanical characteristics of muscle. A new area of evaluation is genetics. Recent advances in molecular genetics, DNA libraries, genetic probes, and gene localization techniques have enhanced the knowledge of neuromuscular disease, including types of muscle dystrophy, Charcot-Marie-Tooth disease, and familial amyotrophic lateral sclerosis. That leads us to aging and the musculoskeletal system. Aging of bones. Aging is accompanied by the loss of bone tissue. Bones become less stiff, less strong, and more brittle with age. The bone remodeling cycle takes longer to complete, and the rate of mineralization also decelerates. Studies have shown that an individual's bone mass at the end of the growth period helps determine the significance of bone loss as the person ages. With aging, women experience loss of bone density, accelerated by rapid bone loss during early menopause from increased osteoclastic bone resorption, fewer osteocytes, and decreased number of osteoblasts. By age 70 years, susceptible women have on average lost 50% of their peripheral cortical bone mass. Bone mass loss as the extent can lead to deformity, pain, stiffness, and high risk for fractures. Men also experience bone mass loss, but at a later age. Excuse me, but at a later age, at much slower rates than women. Also, peak bone mass in men is higher than that in women. Therefore, bone loss in men causes less risk of disability than for women. In general, age-related bone loss is caused by genetics, hormonal factors, decreased bone formation, vitamin and mineral deficiencies, underlying conditions, and lifestyle choices. Men's peak bone mass is related to race, heredity, hormonal factors, physical activity, and calcium intake during childhood. Height is also lost with aging because of intervertebral disc degeneration and sometimes osteoporotic spinal fractures. Bone mass can be gained in healthy young women up to the third decade through physical activity and intake of dietary calcium and magnesium. In postmenopausal women, aerobic exercise and strength training in particular have proven to be effective in improving and maintaining bone mass during the aging process. In addition to the positive effects of exercise on bone mineral density, exercise is shown to improve balance, coordination, muscle strength, lean body mass, and mobility, all of which decrease the incidence of falls. Aging of joints. With aging, cartilage becomes more rigid, fragile, and susceptible to fraying because of increased cross-linking of collagen and elastin, decreased water content in the cartilage ground substance, and decreased concentration of glycose aminoglycans. Changes in collagen result in cartilage calcification and muscle stiffness. Decreased range of motion of the joint is related to the changes in ligaments and muscles. Bones in the joints develop
evidence of osteoporosis with fever, trabeculae, and thinner, less dense bones, making them prone to fractures. Innervated disc space decrease in height. Aging of muscles. The function of skeletal muscle depends on the many factors that are affected by aging, including the nervous, vascular, and endocrine system. Mitochondrial dysfunction within cells contribute to oxidative stress and results in increased bone resorption and apoptosis of muscle cells. In the young child, development of muscle tissue is highly dependent on continuing neurodevelopment or neurodevelopmental maturation. Muscle function remains trainable even into advanced age. Muscle disease have a definitive association with specific age groups. Muscular dystrophies occur in children, and muscle disabilities related to rheumatic disease usually occur in advancing age. Age-related loss in skeletal muscle is referred to as sarcopenia and is a direct cause of age-related decrease in muscle strength. By 50 years of age, roughly 10% of muscle area is lost. Parallel to sarcopenia, muscle strength declines by 15% per decade in the 60s and 70s and doubles to 30% after 80 years of age. As the body ages, muscle bulk and strength decline slowly, beginning as early as age 50, with loss of about 1% per year thereafter. Muscle strength declines faster than muscle mass. Type 2 fibers decrease to a greater extent than the slower type 1. Loss of satellite cells appears to play a major role in the development of sarcopenia, although muscle degenerative function remains largely intact. Satellite cells numbers are decreased. Reduced RNA synthesis, loss of mitochondrial volume, shortening of telomeres, and reduction in the size of motor units contribute to sarcopenia. As much as 30 to 40% of skeletal muscle mass and strength may be lost from the third to ninth decade. Maximal oxygen intake decreases with age. Reduced basal metabolic rate and decreased lean body mass are also seen in the older adult population. And that concludes our chapter for today. I will see you with the next chapter, 45, alterations of musculoskeletal function, though we will stop at bone tumors. So I shall see you all then. Thank you all for watching, and I'll see you next time. Take care, and goodbye.